So, hello everyone. So my name is Elie CORMIER. I'm a first-year PhD student in the laboratory Hubert Curien. I just started in October, so today my talk will also be with the work I did in an internship before. So today I will present you how we managed to exploit magneto-optic metasurfaces for the exaltation of transverse magneto-optic Kerr effect. So So first of all, I will present you what are magneto-optic effects because it's not a well-known area of optics. And then I will tackle the different part of my project with the results I've got during my internship. So first of all, what are magneto-optic effects? So those effects are really well known in the literature, but they are quite different configuration. So one known effect is the Faraday effect that exists in transmission through a magnetized material. What we observe is a rotation of the polarization plane of a wave after transmission through a material. And it's typically an application of an optical isolator for laser, for example. But for my work, I'm interested into the Kerr effect. So in this case, we are in reflection from a magnetized material. And here, in addition to the rotation of the polarization plane, we also observe a modulation of light intensity. So this Kerr effect is really interesting for us. And we have different configuration. And for each configuration, we have the direction of the magnetic field B in regard to the magnetic materials or the plane incident plane. So we have three configurations. The first one is the polar configuration, longitudinal one and transverse one. Each time I have the corresponding permittivity tensor here for every configuration. And for this topic, I will be interested into the TMOC configuration, so the transverse magneto-optic Kerr effect. Here, for the definition of the permittivity tensor, every time we have a diagonal element which is the same, and what will change is the position of the off diagonal element, epsilon MO. It's always the same value for each configuration, but what will change is the position in the permittivity tensor because of the different direction of the magnetic field B. So, as I said before, those magneto-optic effects are well known in the literature, but they are quite low, and what we want is to find a way to enhance those magneto-optic effects to improve performance and sensitivity of magneto-optic devices. Those effects are used in different applications, such as non-destructive testing, fast spatial modulators, or magnetic sensing and biosensing. As I said, these effects are naturally weak, but they always exist in bulk or in thin film for every magneto-optic materials. What we propose in my work is to couple a waveguide with a magnetic material with a grating. So this is a typical structure I did. So first, we have a waveguide with in green the magnetic thin film. So without grating, we can observe magneto-optic effects, but they will be quite low, as I said. So the idea is to add a grating, here a photoresist grating, and what we will observe is a guided mode resonance, so at a certain wavelength that is given by the coupling equation for waveguide. We will have a resonance, and at this particular wavelength, we will have an increase of the magneto-optic effect. What we observe here is with this type of structure, the evolution of the transmittivity and with the different color, we have in red the theoretical structure without magnetic field. And what we observe is when we put a magnetic field, a positive or negative one, we have the shift of the resonance. Here is a quite interesting observation. What happened is by adding a magnetic field, we change the permittivity tensor of our magneto-optic material, as I explained before, and this will change the coupling equation and most particularly the propagation constant of the waveguide. This effect is shifting the resonance, as we can see in the graph. So it's interesting to have a way to change the properties of a waveguide by varying the magnetic field, and that's what we will use for this work. So here we have this idea of a structure, and I will present you a little bit more in details what magnetic film we'll use. In our case, the magneto-optic material we're using in our team is cobalt ferrites, and more precisely, cobalt ferrite nanoparticles. We have cobalt ferrite nanoparticles, sorry, in a liquid base, the ferrofluid, and next to it in a solid silica matrix. So these nanoparticles are around 10 nanometers diameter. And to have a solid silica matrix, we use a sol gel process to have those nanoparticles embedded in silica matrix. And then we use a deep coating technique to have a solid layer. So here are the transmission electron microscopy images observation. And what we have here is stabilized nanoparticle in both configurations. So what we're interested in is the magneto-optic effect of our material. And we have here the evolution of the Faraday rotation of cobalt ferrite. Here we can directly link this Faraday rotation with the off-diagonal element epsilon MO. So the magneto-optic effect will be at a maximum where we have a maximum value of the Faraday rotation to simplify the idea. So here we have two areas of interest with a maximum, but the one we will choose is the one between 1400 and 1600, because as I said, it's a maximum of Faraday rotation, meaning we have high magneto-optic effects. And also in infrared, we have low absorption in comparison to the visible one here. So we will try to have a structure with a resonance around this, in this area of interest. Now that I introduced you magneto-optic effects and material, I will go deeper in my work and with the fabrication process of my sample. So as I said, the first step is to have our magneto-optic layer with sol gel and deep coating technique. Once we have our solid layer, we did multiple process in the platform Nano Saint-Étienne in the lab. So first one, we have we use a spin coater to have our photoresist layer. Once this one is ready, we can use the microwriter device to do the UV exposition. For that, with the software, we can easily create our grating, and then the microwriter will automatically expose every area of our sample to create the grating we want. So after exposition, we can reveal our grating with the etching process. After all this step, we have our sample and it's ready to do characterization. So here is an example of one sample after etching. So we observe the grating with here the specular diffraction. So it's a nice area. In this area, we use an atomic force microscope to do observation and measurement. So first we have the topography of our layer. Then we have access to the profile, and with the FTT module, we can have access to the period of our grating. So with all this measurement and observation, we were able to conclude about our structure. So we have a grating with a period around 2.7 micrometer. That was a value we aimed for this fabrication process, so we were really happy to have that. And also we have a grating with a depth around 300 nanometers. Once again, it's a nice result because it's around 80% of the total thickness of the photoresist layer. And in our case, it's important to maximize this value. So with that, we can now do the final characterization with ellipsometry measurement. So here's our setup. We have here our sample with a magnet. So we can do measurements without magnetic field and with magnetic field. We can flip the magnet to have a positive or negative magnetic field. And what we are interested in is the two ellipsometer angles, so psi and delta, and they are directly related to the amplitude of the parallel and perpendicular component of the incident wave after reflection for psi, and for delta, the same, but with the phase differences between the two components. So what is interested in is we have a way to understand the coupling between the the parallel component and perpendicular component of our wave after reflection. As I said, our area of interest is between 1400 and 1600. And here we observe the evolution of the two ellipsometrical angle psi and delta. And we have a nice effect around 1500. Here, what is interesting is to observe that we have a huge shift, a huge effect. Here we know, thanks to that observation, that something is happening at that wavelength. And this is an effect coupling that is related to the coupling between the parallel and perpendicular components. By observing this, we know that something is happening, and we can relate that to the magneto-optic effects, but it's not directly what we observe here. And what we need is to define the TMOC. So that's the definition of the TMOC. For that, we need the intensity of the reflected light in three configurations. So without magnetic field, with a positive magnetic field, and with a negative one. Another way to observe that is by using the definition of the intensity using the RP component of the wave. And we have the TMOC related to the ellipsometric angle psi. So after that, I was able to plot the evolution of TMOC in the same area of interest. We have in orange the simulated one and in blue the experimental one. What is interesting is that the two are really close to each other. The main differences can come from a difference between the structure theoretically and the one we fabricate, because there are always difference in the thickness of every layer or our grating. But the main idea is that we successfully obtain a TMOC up to 38%. That it's a huge effect because, as I said in the beginning, magneto-optic effects are quite low naturally. And for example, TMOC without resonance can be around 1% and even less than 1%. So it's really impressive to have a high TMOC effect here. So the experimental value is current with the simulation, and we successfully enhance the TMOC effect in this area of interest. So that concludes my work in this project. So to sum up, we have a high TMOC in around 500 nanometers. We have a good fabrication process and a way to do simulation effectively. But what is interesting is that is kind of the basis of for my thesis and my PhD. So most of this work have been done during my internship. But now I need to go deeper and into more complex patterns with 2D or chiral patterns such as this one. With that, we'll have to test other photolithography techniques because using the one I did it was pretty simple for an internship, but it's limited, and I need to have something with a higher resolution. And the idea in my thesis is to tackle some effect hybridization, example with magneto-optic and plasmonic, or in this case, magneto-optic and gyro-optic effects. So this is kind of an introduction for my thesis work, but that's what I've done until here. Thank you for your attention, everyone.
Thank you very much for the presentation and the perspectives. Yeah, are there any questions? Yes, please.
Thank you for this interesting talk. Maybe I missed it. You put two different types of equations for TMOG, right? This one. So what is the difference? Is it corresponding one? Yeah, like maybe you can go over it. And then when you showed experimental and simulation, which one did you use? I guess I didn't get it. Maybe they are on top of each other.
Yeah, it's interesting question. So both, we can use both for simulation later. But here, what is interesting, this is the classical way of defining TMOC. So in the literature, we usually have this one. But in our case, sometimes it can be, for instance, for experimental, we don't have access to the intensity with B equals 0 because our sample is magnetized. We don't have we have a remnant field of our sample, so we don't have access to the intensity without B. So we have another way to define it. As I said, because we are in TMOC configuration, we have P polarization, P configuration, sorry. So we can define intensity like that. And using the definition of ellipsometric angle, and it's something I haven't talked about here, but we have this relation in this case. So it's just something that in S, when we are using the S component of the wave, we observe that is the same even if we change the magnetic field. So just when we do the equation, we have, from that and the ellipsometrical angle, we have this equation, but it's exactly the same as before. Is that clear? And so for the experimental plot or the simulation, we can use both of them. It depends on which value we obtain with the measurement. So with ellipsometry, we have access to psi, so we can use psi. But with simulation, we can directly have access to the intensity, so both are possible.
Thank you for your answer. Any other questions? Yeah.
I don't know if you had time to think about the perspective you mentioned. You spoke about plasmonic and hybridization. What is for you the added value for mixing plasmonic and magneto-optic?
I'm mostly read about magneto-optic and chiroptic hybridization, but I think it can be the same answer. So what can be interesting is by adding another effect, we have another degree of liberty, another way to couple effects. So as I said, sometimes it can be difficult when we just observe magneto-optic effects because they are low, it's difficult to observe them. So we want to couple them with a grating to have an enhancement of it. But another way to have a higher sensitivity, for example, is also to couple it and have a hybridization of effects to observe something else. In the case of chiroptic effects, we can add the polarization, like red, left and right-handed polarization, to improve the observation and try to find another way to have a better sensitivity or better performances. And we can do the same with plasmonic, I think. I don't have much information about it, but it's also a way. Yeah.
Thank you very much. Okay, any other question in the audience, from the audience? Okay, otherwise, I mean, we can thank again Elie for the presentation.